Right, let's get straight into it. Today, we are unpacking an absolutely fascinating and honestly, highly counterintuitive world sitting right at the intersection of physics and manufacturing. We're looking at some brilliant engineering source materials from the Thopper Institute of Engineering and Technology to really understand how the metal objects all around us are made. We're talking about sand casting today. Specifically, we're looking at the hidden genius of casting patterns. Get ready, because the way things are actually built is probably going to surprise you.
So let me ask you a question. When you look at a cast metal object, say an engine block or a heavy iron gear, how do you think they made the mold for it? I think the common assumption is that engineers just make a perfect one-to-one replica of the product, pack some sand around it, pull it out, and pour in the liquid metal. Pretty simple, right? Well, not exactly. Creating a cast metal part is actually this really intricate game of physics, thermodynamics, and incredibly precise compensations. That mold, it is never a perfect copy.
Okay, let's dive into this. To understand why the mold isn't a perfect copy, we really have to look at the unsung hero of the manufacturing floor, the pattern. A pattern is a full-sized model of the part. But here's the twist. It's actually made slightly larger than the final product. Why? Well, because the pattern maker literally has to anticipate the future. They have to account for the fact that metal shrinks when it cools down, and that the surface is going to need to be smoothed out later on. So the pattern is actually an intentional distortion of the final goal.
Moving on to Section 1, Anatomy of a Pattern. What are they made of?
Like almost everything in engineering, every decision is a balance of trade-offs right from step one. There are three main materials pattern makers use. Wood is super common because, well, it's cheap and easy to carve, but it absorbs moisture from the sand and tends to warp over time. Metal, on the other hand, is an absolute champion of durability for high-volume production, but yeah, it's way more expensive to fabricate. And then you have plastic. It kind of steps in as this modern compromise that really balances cost and longevity. The material you choose fundamentally dictates how the pattern is going to behave on the factory floor.
Now, what we're talking about here is a solid one-piece pattern. It's basically the simplest type of pattern you can make. It's relatively cheap to construct since it's just a single geometric block. But because it's just one big piece, the actual process of molding the sand around it and then getting it out can be pretty slow and tedious for the operator. Because of that, solid patterns are generally reserved for simpler shapes and small production runs. Situations where you just don't need to mass-produce thousands of parts every single day.
Which brings us to Section 2, the allowance equation, fighting the physics of shrinkage.
To win that fight against physics, pattern makers use a system of very specific modifications. There are 5 vital allowances that affect the dimensional characteristics of a casting. You've got shrinkage, machining, draft, distortion, and wrapping allowances. And listen, selecting the correct allowances is absolutely crucial. If you get these wrong, you're looking at rejected parts, wasted metal, and skyrocketing machining costs. Today, we're going to unpack the most fascinating ones on this list.
So the really crucial point here is understanding exactly when the metal actually shrinks. When molten metal cools, it contracts in 2 distinct phases, liquid and solid. Liquid contraction happens as the metal cools down to its freezing point. But pattern makers actually don't worry about that. Liquid contraction is handled by adding extra reservoirs of molten metal, which are called risers, to feed the mold. The pattern maker only adds a positive size allowance to fight solid contraction. That's the shrinking that happens after the metal has frozen into a solid shape and continues to cool all the way down to room temperature. And this brilliantly illustrates just how volatile different metals are as they cool down to room temperature. Just look at the variance here. Cast iron is going to shrink about 10 millimeters for every meter of length. Aluminum alloys are a bit more dramatic, shrinking 15 millimeters per meter. And brass? Brass shrinks the most out of these three, sitting at 16 millimeters per meter. So what does this all mean? Well, it means you literally cannot use a pattern designed for cast iron to pour a brass part. If you did, your final brass casting would end up significantly undersized.
But let's look at this as a real-world math puzzle. Imagine we're making a part out of cast iron, which, as we just saw, shrinks at a rate of 10 millimeters per meter. If the blueprint asks for a section to be exactly 100 millimeters long, the pattern maker has to scale it up. They multiply 100 by 10 over 1,000, which gives a 1 millimeter allowance, so the pattern is built to 101 millimeters. For a 160 millimeter section, they add 1.6 millimeters. Every single dimension, no matter how small, even a 25 millimeter tab getting an extra quarter of a millimeter, it all must be calculated and scaled up. It's incredibly precise work.
All right, on to Section 3, Machining and Draft, Preparing for the Real World.
The reality of sand casting is that the surface finish it leaves behind is generally, well, quite rough. If a part needs to fit perfectly into a machine or have this smooth, dimensionally accurate surface, it has to be machined down after it's cast. But think about it. If we made the pattern to the exact final size, the moment we grind it smooth, the part becomes too small. So we apply what's called a machining allowance. We make the pattern even larger, intentionally adding this extra sacrificial metal that we are fully planning to shave away later.
Now I want you to imagine trying to pull this oversized pattern out of hard-packed sand. If the sides are perfectly vertical, meaning no draft, those sides are going to scrape all the way up, dragging and tearing the sand walls, completely ruining the mold. It's exactly like trying to pull a perfectly square, straight block out of tightly packed dirt. The suction and friction just fight you the whole way. But if we apply a draft allowance, which means we taper the vertical surfaces slightly, kind of like a wedge, the moment you lift it even a single millimeter, the entire pattern separates from the sand walls instantly. The mold stays perfectly protected.
To make that wedge-like separation work, engineers adhere to a standard rule. The normal amount of taper on external surfaces is between 10 and 20 millimeters per meter. It's a really subtle slant, often totally invisible to the untrained eye, but it's absolutely essential. It allows the mold to lift out cleanly without the operator having to aggressively shake or damage the sand cavity.
Next up is Section 4, the wrapping exception, the shrinking plot twist.
Now, what's really interesting about this slide is the sheer irony of the situation. To get a pattern out of the sand, even with that draft allowance we just talked about, a molder will lightly tap or shake the pattern to loosen it. This process is called wrapping. But shaking the pattern actually compresses the sand around it, effectively making the empty mold cavity bigger than the pattern itself. So, after we just spent all this time making the pattern bigger to account for shrinkage and bigger to account for machining, we now have to completely reverse course and make it smaller to account for wrapping.
And the exact negative allowance applied for wrapping is typically between 0.5 and 1.0 millimeters. It is a tiny but absolutely vital subtraction. I think it perfectly cements the fact that manufacturing isn't just about tracing lines on a blueprint. It's this continuous, highly intricate balancing act of additions and subtractions, predicting human behavior on the factory floor and anticipating the molecular behavior of cooling metal.
So a casting pattern truly is a masterclass in anticipating physics. It shows us that sometimes achieving absolute perfection requires you to deliberately start with an imperfect, distorted model. Honestly, it makes you look at every metal object differently. If a simple iron block requires shrinkage math, sacrificial machining layers, wedge-like draft angles, and negative wrapping allowances just to exist, what other hidden, invisible engineering compensations are quietly shaping the everyday objects all around us? Think about that the next time you pick up anything made of metal. Thanks for joining me on this explainer of the source material, and keep questioning how the world is built.